Now in this lecture we will see one of the geometric algorithms. There is a plethora of geometric problems, and algorithm plays a vital role in solving those problems. Generally both the analysis and design. It's a very good example or area of problems where you can really apply the techniques, algorithmic techniques, to design efficient algorithms. So what we will do, we will just pick up only one problem from this geometric problems, which is called the convex hull computation. This is a very important problem in geometric area. So let me first define what is a convex hull. Suppose we have been given a set of points in 2 dimensions. And the convex hull of this point set is defined as the smallest convex polygon or which contains this entire set. So if I draw it, I will not draw the convex hull right now. You just think about what is the smallest convex polygon which will contain all the points inside or on it. Which I'll leave it to you for the time being. But first let me define what is a convex set. A convex set in plane is a subset of the plane such that if you take any 2 points in that set, the entire line segment lies within that set. That is the definition of convexity. So like this one, this set is a convex set, because if I take any 2 points, say here and here, the entire line segment is lying within the set. But for example, you take this is not anymore convex, because if you take say this point and this point, then this line segment is not lying within this entire set, because this part is out. So this is not a convex set. So the definition of convex set is exactly this. So I am going to define convex hull in terms of the convex set now. So the convex hull of a set of points S given in R2. R2 generally signifies the plane, real plane. That's why R2, 2-dimensional plane. That's why 2. R signifies the real points. 2-dimensional plane is generally denoted as R2. Then the convex hull of a set of points in R2 denoted as conv S. This is the notation I will be using. Is the smallest convex set R, so that S is a subset of R. So this is the smallest convex set which contains the entire point set inside. So given this point, what is the convex hull? The smallest convex set, I am going to draw it now. Join this and this and this.
The smallest in terms of area, number of points.
It's not the number of points. Okay, let me define this. First of all, this set is an infinite set, because there are infinite number of points in the plane. It is the smallest in terms of the area. And this. So this is the smallest convex set which contains all these points inside or on. You cannot draw anything else. And I am assuming no 3 points are collinear for the time being. because that's not a very general position. I'm just assuming that only 2 points are collinear, has to be, no 3 points are collinear. So this is the smallest convex set. This is the convex hull of these points. So let me draw some more pictures to give you the idea of a convex hull, because it need not be so nicely symmetric. So suppose I have been given this point set. For this one, the convex set is, to join this and this, the convex hull I am drawing this. So this is the convex hull of this point set. If I did not have this point, suddenly the convex hull will change a lot. You should have observed this. Suppose this point was not there in the point set, then the convex hull would have taken this, probably this and this. So this would be the convex hull. So whether a point is there or not, that may make a lot of difference in the convex hull configuration. So the problem is, given a set of points as coordinates, xy coordinates, we are required to find out this convex hull. Now convex hull is a two-dimensional entity, because it's a convex set in, is a subset of plane. But if we compute only the boundary of the convex hull, it will be enough for us for the representation of the convex hull, because this boundary itself will represent the entire inside. So what we mean by convex hull computation is to compute the boundary of the convex hull given the set of points S in the plane. So that is our problem, how to do it efficiently. Actually there is another way we can define the convex hull, which basically all the points inside the convex hull can be defined as the convex combination of the points given inside the convex hull. So if you take the points, given points, the set S, and any point in the convex hull should be a convex combination of those given points. What do we mean by convex combination? Is this. So suppose we have been given 2 points, or say S is equal to say P1, P2 up to say Pn, then convex combination, which again will be same as conv S, convex hull, is nothing but all the points in X are 2, such that X is equal to, this is a convex combination, it is the summation of linear combination, I is equal to 1 to n lambda I pi, where all lambda I is greater than equal to 0 and sigma of lambda I is equal to 1 to n is exactly equal to 1. This is called the convex combination. So if there are 2 points, what is the convex combination of these 2 points? Is nothing but this, all the points joining this segment, which are lying on this segment. So if there are 2 points, say A and B, any point X you can always write for this one as lambda A probably plus lambda 1A, lambda 2B, where lambda 1 plus lambda 2 is equal to 1 and each lambda I is greater than equal to 0. Each point inside this AB you can express like this. What you have seen this form, lambda A plus 1 minus lambda B. Vary lambda you will get all the points, but here lambda 2 is nothing but 1 minus lambda. From here lambda 2 is nothing but 1 minus lambda 1. So the convex combination of 2 points is nothing but the segment joining these 2 points. Similarly, convex combination of 3 points are all the points inside the triangles. Any point inside the triangle you can always express it as lambda 1 A plus lambda 2 B, so A, B, C, lambda 1 A plus lambda 2 B plus lambda 3 C, where lambda 1 plus lambda 2 plus lambda 3 is equal to 1. So this is nothing but generalization of this, what I just said. If there are n points, then you take the convex, this is called the convex combination, where with this constant they add up to 1 and each one is greater than or equal to 0. And convex hull, another definition is basically is the set of all points which are the convex combination of the given points. Now I am going to give one algorithm for computing the convex hull. There are several algorithms for computing the convex hull. I am going to tell you only one of them, which is called the plane sweep algorithm. Before I go into the details of this algorithm, let me just tell you why it is named like this. Plane sweep is the algorithm will proceed as if we are sweeping the plane from one direction to the other. So the plane has been given, suppose we are as if we are going from say left to right. We will go from left to right and take actions as we go along. So we will be seeing the points from left to right one by one, and we will take actions, we will update our convex hull as we see a new point. And when we have reached the rightmost point, we will be done with the convex hull. So as if we have taken a line, a vertical line, and as if this vertical line is shifting like this, and that's why it's called the sweeping. You are sweeping the plane, entire plane. We will not do the entire plane because we don't need to. We have to be worried only about those positions where this line will hit a point. All the other positions are immaterial for us for the computation of the convex. But the name comes from this, as if we are just looking through a line and this line is moving from left to right like this. That's why it's called plane sweep. So now let me tell you how the algorithm proceeds. Again, as I told you, we will be moving from left to right. So first what we do, we sort all the points from left to right. So you take the x, say suppose our x coordinate is this, y is this direction, suppose, then we will be sorting all the points with respect to say increasing x coordinates. So we will start from the leftmost point, and then we will be having, we will process the point one by one in this sorted order. So I am assuming now S P1, P2 up to Pn are sorted with respect to their x coordinate. Okay. Now what I will be telling you, when we reach in a generic state, when we reach a point say Pi, and suppose till then we have already computed the convex hull of all the points from P1 to Pi minus 1. So we assume that the convex hull of the points from Pi to Pi minus 1 has been computed, and we are going to take the next point in this sorted order, which is Pi. And what would we do? If I can tell you this, then you can basically iterate over all the points in this sorted order. So this is the most generic step which we have to deal with properly. So let us see, suppose we have got this convex hull up to the point say Pi minus 1. So Pi minus 1 is say this one. So this is the point Pi minus 1 which has been added the last. Now suppose we are going to get Pi somewhere here. So this is the next point. So you have to see what do you have to do to update this convex hull. So can you tell me what are the things which you have to determine for to update this convex hull? It's not the slope of the previous line. We have to determine basically the tangent from Pi to this on the upper side, the tangent from Pi to the lower side. And these two edges will replace the edges in between them, and that will be your new convex hull. So the new convex hull with pi basically here probably is this one. This is the tangent from pi, and on the lower side this is the tangent. So you have to determine these 2 points where from pi the tangent to the convex hull is going to hit. So once you have done this, then your new convex hull will be nothing but this, then this, and you have to delete this part. This is the precise action we have to do. We have to determine this is called the upper bridge or upper tangent, and this is the lower bridge or the lower tangent. Once these 2 tangents are determined, we have to, the next step is very trivial. We have to just add these 2 properly to the already computed convex hull and delete the portion in between them. So you have got the new convex hull now with the point pi. Then again another point may come here. You have to determine again these 2 tangents, take this action. Go on until unless you finish all the points. All right. So this is the action we have to do. Now let us look a little bit more general case of determining this 2 bridges, upper bridge and the lower bridge, or upper tangent and lower tangent. In a very generic situation, what will happen is this, and probably your point pi is here, and your convex hull is something like this, and your say last point pi minus 1 is here. So in this case, first we know pi, we know pi, and we also know what is pi minus 1. That must be on the convex hull already, because that is the rightmost point. Rightmost point has to be on the convex hull so far. So what we do, first we join this line segment. We take this line segment pi minus 1. Then we move up. We see whether this edge and this edge makes a right turn or a left turn. If it is a right turn, then this cannot be a bridge. You can see this is a right turn, then this edge cannot be a bridge. For this edge to be bridge, it has to be a left turn. So let us see. So this is this, then I am taking a right turn. So this I know immediately this point cannot give me the proper bridge at this point. So this is also not a bridge, but we have moved up. I know that the bridge is actually higher up. So now you do the same thing. You see this and this. This is also a right turn. So again this at this point. So I know. So immediately I know that this cannot. Sorry, let me go back a little bit. Since this and this is a right turn, I know this one is not a bridge. I can take that decision. Then take the next one. This and this is a right turn. So this cannot be a bridge. Now go to this point. You take this. Then the next stage is this. Then suddenly you can see this and this is a left turn. It's not anymore right turn. It's a left turn now. So immediately we know that this has to be the upper tangent. So that's the algorithm. That's the way we will find out what is the upper tangent, what is the lower tangent. Let us look at the lower side. How would you do? First I take again this one. I know that this and this. So now it will, the role of left turn, right turn will be reversed. You see this and this is a left turn. So now we are trying to find the lower tangent, then it is not a bridge. It has to be right turn, then only it will be bridge. Now look at this and this. Again left turn, this cannot be a bridge. Let us take the next one. This and this is a left turn. Again this cannot be a bridge. Take the next point. Now this and probably this, I am just assuming, then it is a right turn. This, if it is not, then basically it should go next. But let me draw it little. Suppose the point is like this. So suppose this and this is a right turn. In that case, this is the bridge. So as if you are walking, you started from this segment joining pi and pi minus 1, you are walking up. You are walking up and seeing whether it is a left turn or a right turn. The first, on the upper side, the first left turn will give you the upper tangent. Similarly, on the lower side, you start walking. The first right turn will give you the lower tangent. So you do this walking on both sides, determine these two tangents, then you update your convex hull. So this is what the algorithm will do. Now let me first tell you the pseudocode for this algorithm. Then I will explain how to compute the left turn and right turn. So this is the pseudocode. First, one step is sort points from left to right. Which gives P1, P2 up to Pn. Second step. So how do you start? I know if there are the first 3 points, the convex hull is nothing but the triangle. So I can compute the first convex hull because we have to iterate. So I need to know the convex hull already computed. So first 3 points, we compute the convex hull straightforward, the triangle itself. So compute or construct the triangle conv P1, P2, P3. Then the third step, this is the for loop. For I going from 4 to n, do add pi to conv P1, P2, pi minus 1 by finding the two tangents from pi and 4. This is a very high level language, high level algorithm. I will explain. I have already explained this step, but this I will write down later. How to find these two tangents I have explained, but I have not given the pseudocode. I will give you the pseudocode later. But this is the entire iteration. From 4 to n, we have to do it again and again. So now, to tell you how to do this left turn and right turn, we compute this quantity. Suppose A, B, C are the 3 points. So I am assuming A, its coordinate is ax, ay. There is a point B, bx, by. There is a point C, cx, cy. Then to know whether, so I have basically I have this thing. Say this is A, this is a B, this is a C. I need to know whether A, B, C makes a left turn or a right turn. So if you compute this determinant ax, ay 1, bx, by 1, cx, cy 1, compute this determinant. If this determinant is greater than 0, then it is then ABC makes a left turn. If it is less than 0, then it makes a right turn. If determinant is less than 0, then right turn. And if it is 0, then all the 3 points are collinear. So exactly, so determinant exactly 0, ABC are collinear. So by computing this, you can compute whether 3 points are making a left turn or right turn. And this computation is a constant time affair given the 3 points. It's a determinant computation. Now, let me assume how do we represent the convex hull inside the computer. What we will do, we can represent the convex hull as a linked list, circular linked list, and assume a doubly linked list, because we need to move both in upper direction and the lower direction. So it's a doubly linked list which will assist you in that. So we are going to represent the entire convex hull using a doubly linked list, circular doubly linked list. Okay, and each pi will be a structure. Each pi will be a structure. What it will have? The three fields it will have. One is the vertex of pi, vpi. This will give you basically the coordinates. Then I will be assuming next of pi, another field. Next of pi basically the forward link in the circular linked list. Similarly, prev of pi, the other link, because since it is a doubly linked list. So these are the three fields I will be assuming. Now I am going to write the algorithm for finding the tangents, which I just told you. I am assuming that we have a pointer to the point which has been added the last. So that is pi minus 1. So I am going to write the tangent finding algorithm. Suppose u is equal to last. So last has been already is known to us. That is the last point. U is last. Now while, that walking is nothing but a while loop. You go on walking up until unless you hit this left and right arm exchange. So while pi v of u and v of next u. So v of next u is in this algorithm. Let me see. So here this is pi, this is your last. So pi, your u, next of u is this. So if this is a right turn, then we move forward. Do u is equal to next u, and while. When this while loop terminates, the value of u will be nothing but the point where the tangent hits the convex hull. This is the walk upward. This is the walk upward. Similarly, we will have a walk downward. So again we initialize L is equal to last, while pi v of L, v this time prev pointer we have to take, because we are moving down now. This is the prev pointer. The upper one I assume the next pointer. Prev L is a left turn. Then you do this thing. Do L is equal to prev L, and while. This will give you the point where the lower tangent will hit the convex hull. This is the upper, this is the lower. Once you have found this, then basically you have to set those two edges. So set v of, I am assuming pi actually w, or let me put it as pi. V of pi is, or let me put this one as w, the pi. So basically my configuration is here. So I have updated this. So this is my pi. So I have determined these 2 points. So these 2 points, this is actually u, and this will be your L, and this I am assuming as w. So v of w is equal to pi. When I say pi, basically the x coordinates. You are just setting this x coordinates. Then you have to say next of w will be u, and prev of w will be L, and similarly you have to do prev of u is equal to w, and next of L is equal to W, and this will compute your convex hull. You have updated the convex hull. So this will update your convex hull. So this part you plug in into the original algorithm where you are trying to find out the upper tangent and lower tangent. That will give you the entire convex hull computation. Now let us see how much time does this take. Yes. So somebody has already observed that it is n square. Why? Why it is n square? Because let us see. At each point of pi, we are going to walk up or walk down. And how many points we will be walking up and walking down at most? It can be in the worst case n or I minus 1, right? In the worst case n, but actually it will be I minus 1. So in that case, the total complexity will be 1 plus 2 up to n. So that will give you the order of n square. Okay, so this algorithm is an order of n square algorithm, but that is not right. Why that is not right? I will tell you, because our analysis is not correct. We analyze the algorithm very pessimistically. So we can, and here is the power of learning how to analyze algorithm. This algorithm is quite good, otherwise you will discard this algorithm if you don't analyze it properly. Actually it is taking only order n log n time. And I tell you the logic why it is not order of n square. It is a very one line argument and tells you everything. Let us look at the complexity of this tangent determinant. If we have walked towards say k points, suppose if we have walked toward k points, this step takes order k time, right? This takes order k time. But look at this, if there are k points, we are deleting also k minus 1 points, and this k minus 1 points will never reappear in the computation at all. Those points which you are deleting, like this part here, this will never come and reappear in the computation again. So if you are spending k times here, order k times, then you are deleting also k minus 1 points which will never reappear. So as if each point is getting a charge of 1, because this deletion, suppose you charge the point for this deletion. So each point is getting a charge of 1 because it is not going to reappear again. And if I compute this charge over all the points, that will take care of all the entire complexity. And if each point has got a charge 1, what is the total charge? Only order n. So even if each incremental step can be order n, each incremental step can be order I am not denying that. But the overall complexity, the total complexity cannot exceed order n. At least this tangent computation. The logic is, so I am going to write now. Two while loops, if two while loops go over k points, then k minus 1 points are deleted from the convex hull. Since each point is deleted at most once, this is the catch, each point is deleted at most once, the total time for constructing con S, where S is equal to n, is order n after sorting. So together with the sorting, the convex hull computation is, so the total time complexity is how much? Order n log n. It is the sorting time which is giving you n log n. The tangent computation still is order n over all the tangent computations. Okay, and probably you may have a question whether this can be further reduced. It cannot be further reduced. This problem has the lower bound of n log n. This problem I am saying, not this algorithm. This algorithm also n log n definitely, but this problem itself also has a lower bound of n log n. You cannot have an algorithm for convex hull which can take less than n log n time, because the problem of sorting can be reduced to this problem. If convex hull, it means if convex hull can be computed in less than n log n time, sorting also can be computed in less than n log n time. But we already know sorting cannot be done in less than n log n time. So this says that convex hull cannot be done in n log n time. So we have solved this problem optimally now. This problem cannot be solved less than n log n time, and we have given an algorithm which takes order n log n time. So this problem has been solved in optimal time. So again I repeat, this analysis is very crucial, and this is a perfect example why you should analyze your algorithm properly, because design is dependent on your analysis. Otherwise you would have discarded this very easy algorithm. And there is no hard and fast rule. The analysis is a little bit careful checking of what is happening. Now let me just finish by making a remark. This entire convex hull computation can be done using a divide and conquer technique. So you just divide the point set into two equal halves, and then you check what to do for this. So I leave it to you. You think over it, how to do the convex hull using a divide and conquer technique. Again, that should take, again I leave it to you. How much time does it take? How you should design that? You should analyze it properly and everything. So this is the one geometric algorithm we will cover in this course. There are, again I told you, there are many such geometric algorithms which are very interesting in terms of analysis and design paradigms, but we don't have the ample time